the null space and then the nullity, and then rank and nullity theorem, and then we study the properties of rank of A plus B less than or equal to rank of A plus rank of B greater than or equal to rank of A plus rank of B minus n. Okay. So, and then we discuss what is the characteristic polynomial. So, what is the characteristic polynomial is nothing but determinant of A minus xi is the characteristic polynomial of n by n matrix. Okay. So, now, so we usually take P of x is nothing but we call define determinant of the matrix A minus xi is called characteristic polynomial, called the characteristic polynomial of the matrix A. If it is A is an n by n matrix, the degree of P of x is n. Okay, and then the Cayley-Hamilton theorem says this matrix satisfies its matrix, that is every square matrix A satisfies its characteristic polynomial, that is P of A equal to 0. That is very important things. And then the roots of P of x are called that is roots of characteristic polynomial are called eigenvalues or characteristic value. So the roots of the characteristic polynomial of a matrix, characteristic polynomial of A are called eigenvalues or characteristic value. Eigenvalues or characteristic values of a matrix or characteristic roots or values. There are so many names: characteristic roots or characteristic values. Values of A. Now, once we know the eigenvalues, then we can easily say the determinant and the trace is very important property. So we define the determinant of the matrix is nothing but the product of the eigenvalues. So if you know all the eigenvalues, you can easily say the determinant. So product of all eigenvalues is very, very important. Eigenvalues. And then the trace is nothing but sum of the eigenvalues. Here, the trace of A is nothing but sum of all eigenvalues. Okay, and then we studied how the characteristic polynomial look like. If you take any 2 by 2 matrix, the characteristic polynomial is of the form x square minus trace of A times x plus determinant of A. We call P of x. So this is a characteristic polynomial of any 2 by 2 matrix. And then we can extend to the 3 by 3 matrix. The characteristic polynomial of any 3 by 3 matrix is of the form, we can write x cube minus trace of A x square plus actually we can write trace of adjoint of A, trace of the matrix adjoint of A into x minus determinant of the matrix. Or instead of finding the trace of adjoint of A, we can take 1 by 2 trace of A square minus trace of A square. You can use anything, only the coefficient of x. Okay, either you can, anyway both are same, but you have to find the adjoint of A. Instead of that, first take that trace and then square it, and then find the A square and then take the square and subtract it and then divide by 2. So this is a characteristic polynomial of any 3 by 3 matrix. And then I said that there is some given any polynomial, we can give a matrix whose characteristic polynomial as well as the minimal polynomial is the given polynomial. That matrix is called companion matrix. Okay, companion matrix is a very important one. What is that? Companion matrix. So companion matrix is of the form. So companion matrix of a polynomial. So given some polynomial, suppose f of x is given, it should be monic polynomial. Given any monic polynomial, xn an minus 1 x power n minus 1 and so on plus a1x plus a naught. So we can find a polynomial, we can find a n by n matrix whose characteristic polynomial is this f of x. So we call that matrix is companion matrix. So how we define that? You have to take the first row is 0 0, up to n minus 1 column. The last column you can take the negative of the constant polynomial, and then remaining these n minus 1 columns we have to take identity matrix. Identity matrix of order is n minus 1. So the last column is minus a naught minus a1 minus a2 up to minus a n minus 1. Okay, this is an n by n matrix. Okay, so here we have to fill the identity matrix, but order is n minus 1 cross n minus 1. Now the characteristic polynomial of this matrix is this given f of x. So characteristic polynomial as well as the minimal polynomial of this matrix is f of x. Okay, it's very important thing. Okay, so now we are going to define what is eigenvectors of a matrix. So eigenvalue is nothing but the roots of the characteristic polynomial. Now we are going to define what is eigenvector. So after we studied linear transformation at all, we will define eigenvectors in some other different way. But anyway, everything is equivalent. Now we define what is eigenvector. Suppose A is a square matrix, n by n matrix, and we can find a eigenvalue because the determinant of A minus xi, roots of the polynomial is eigenvector. Suppose A is given, so A is an n by n matrix, and suppose lambda is an eigenvalue. Lambda is an eigenvalue. Lambda is an eigenvalue of A. Then there is a non-zero vector. So there is some V is non-zero such that suppose we satisfy the equation A into V. V is a vector. Okay, so V is a vector. So V in Rn. There is a V in Rn, non-zero Rn, such that AV equal to lambda times V. Then this V is called eigenvector of A corresponding to the eigenvalue lambda. So there is a non-zero vector V such that AV equal to lambda V is called eigenvector. Eigenvector of A corresponding to the eigenvalue lambda. Corresponding to the eigenvalue lambda. So given any eigenvalue, we can find a eigenvector corresponding to that. Corresponding to the eigenvalue lambda. Okay. So we can find many non-zero vector V satisfy the equation AV equal to lambda V. Therefore, this V is not unique. For given single eigenvalue, you will get infinitely many eigenvector. Okay. So how to find this eigenvector? So eigenvector means what? Is satisfy the equation AV equal to lambda times V. So we have to find such a V. So we know lambda, we know A. So how to find this V? Suppose V exists. Now that means what? That V satisfy the condition AV equal to lambda V. Okay, AV equal to lambda times V. Okay. So and this V should be non-zero. Therefore, if you simplify these, we can take this lambda V that side, left hand side, we get AV minus lambda V equal to 0. Okay, since we can by matrix, so lambda V is nothing but just a vector. Suppose V is a vector, maybe it's n vector V1, V2, etc. Vn. So lambda V means what? You have to multiply lambda to the each coordinate. That is lambda V. But V is a vector, position of n position. Now we can take rewrite this A minus lambda I times V. You can take V outside, we get this one. Now this is a system of equation. So this is a homogeneous system, right? So instead of Ax equal to B equal to 0, here we have this is our matrix and this is our vector x equal to 0. So we have to find a solution of this homogeneous system of equation. That solution is called eigenvector. If the non-zero solution, because V equal to 0 is always solution, but we need a non-zero solution of the system of equation. Therefore, now how we define the eigenvector? The non-zero solution of the system of equation. So maybe another way you can define the eigenvector. So eigenvectors are the eigenvector corresponding to the eigenvector corresponding to lambda is the solution of A minus lambda I equal to. So the eigenvector the eigenvector corresponding to the eigenvalue corresponding to the eigenvalue lambda is eigenvalue lambda. The eigenvectors, okay, and the eigenvectors corresponding to the eigenvalues are eigenvalue lambdas are solutions of non-zero solutions of the system of equation A minus lambda I times x equal to 0. If we take all non-zero solution of the system, that is the eigenvector corresponding to the eigenvalue lambda. Okay, we know how to solve the this equation, right? So either you have to apply row reduced echelon form to reduce this complicated system into a simpler system, and then either you can apply the back substitution method or forward substitution method. You will find the solution. For example, if you take some special example, we will discuss some example to find the eigenvectors of here. So therefore, each eigenvalue we have eigenvector. So not only unique, it may be infinitely many. Okay, now we will discuss some example to find the eigenvector of a matrix. Okay, suppose if we take some special matrix, any matrix, can anyone say? Suppose I take special matrix 1, 1, 1. All entries are 1. So this is a special type of matrix even. So can anyone tell me what is the eigenvalues? So before that, what is the determinant of the matrix A? Is
0,
anyone?
sir.
0. Very
0,
good.
sir.
Okay. What is the trace of the matrix?
3.
3. Now, what can you say about eigenvalues to this information? Suppose you know the determinant is 0. What can you say about eigenvalues? Because determinant is the product of the eigenvalues. The product is 0. Therefore, 0 means what? All the eigenvalues 0?
And the sum is 3, sir.
The sum is 3. Therefore, at least one eigenvalue is 0, but not all the eigenvalues are 0. Right? So, therefore, 0 is one of the eigenvalue. 0 is an eigenvalue because we get determinant 0. Therefore, product of the eigenvalue is determinant. Therefore, product here 0. Therefore, 0 is the one of the eigenvalue. But what is the rank of this matrix? What is the rank of this? 1. And what is the nullity? By rank nullity theorem, nullity is 2. Therefore, there are so the 0 is a eigenvalue with multiplicity 2. Therefore, we have only one non-zero eigenvalue. So therefore, since the dimension of the nullity is 2, therefore 0 repeated 2 times. That means 0 is an eigenvalue and the multiplicity is 2. 0, 0. Okay, anyway, you will find the, so if suppose how to find these, you find the characteristic polynomial of this. Okay. So what is A square? This is A. What is A square? Anyone? 333. Correct? Correct or? Yeah, because you multiply with the same entry 1, 1, 1, 1, 1, 1, 1, 1. Now this row into this column, multiply this 1 into 1, 1 plus 1 into 1, 1 plus 1. So is everything we get this A square equal to this. Okay. Now, actually, what is this actually? This is nothing but 3 times A. Okay, A square, therefore A square satisfies the condition that A square equal to 3 times A. That means what? A satisfied the polynomial x square minus 3x. Correct? Suppose we take some m of x. So this is nothing but actually if we take x outside, we get x into x minus 3. But this is a 3 by 3 matrix. But we get a second degree polynomial satisfy the matrix A. Therefore, this is a minimal polynomial, but it is not a characteristic polynomial, right? So anyway, we know the general formula of the characteristic polynomial of 3 by 3 matrix. What is that? X cube minus trace of the matrix is 3 times x square plus 1 by 2 times trace of a square. So trace of a is 3 square is 9 minus trace of a square. So 3 plus 3 plus 3 is 9 into x, and then plus determinant. So clearly determinant is 0. Therefore, now we have only x cube term and x square term. So therefore, x cube minus 3 times x square. Now if we take x square is outside, x square into x minus 3. Now what are the roots of this? Since x square is a factor, therefore 0 repeated 2 times and 3 is a root. Therefore, the roots of the polynomials are 0, 0, 3. Therefore, these are the only eigenvalues. Otherwise, if from the rank nullity theorem, the dimension of the that is the dimension of null space is 2. Therefore, there are two eigenvalues. There are 0 eigenvalues. The multiplicity 2. Since rank is 1, we have only one non-zero eigenvalue. So therefore, now we found that the eigenvalues are 0, 0, 3. Okay, now we have to find the eigenvector corresponding to you can take 0 or you can take 3. So better we take 3. So what is the eigenvector corresponding to 3 is nothing but the solution of a minus 3i times b, or x, you can take anything. So first we have to find the solution of this equation. So we take v equal to v1, v2, v3 because this is an element in R3. Therefore, should be ordered triple v1, v2, v3. So what is a? We got to subtract 3 times I. So therefore, the diagonal we got to subtract minus 3. Therefore, we get minus 1, 1 minus 2, 1, 1, 1 minus 2, 1, 1, 1 minus 2. That is a minus 3a. Into v is nothing but v1, v2, v3 equal to 0, 0, 0. So this is the equation. Now we got to find the solution, but it's very difficult to find. Therefore, we have to simplify this matrix into row reduced echelon form. So better I take the matrix. So first you write this matrix here. So 2 or minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2. So since the first row, the first entry is not equal to 1. So therefore, better we interchange the second row and the first row. So therefore, I write the second row first and then the first row by second. And I interchange it. Because this is a elementary row operation. We can interchange two rows, right? Therefore, now I interchanging first row and then second row. Interchanging to this now. Now, we get the first non-zero entries, we get 1. Therefore, we have to make this entry 0 and then we make this entry 0. So, for the last row, just we got to subtract from this, we keep the first row now. I got to make the second row by what I am going to do. Multiply 2 by the first row and then add to the second row. So the first entry is 2, multiply by 2 by 2 plus minus 2 is 0 here. And here already minus 2 there. If you multiply 2, we get minus 4 plus 1 is minus 3. And this one is 2 plus 1 is 3. What about this? The third row I am going to make, if you want to take R1 minus R3. So therefore 1 minus 1 is 0 and that is minus 2 minus 1 is minus 3 and this one is 1 minus 2 is minus 1. Now we did the first row because the first row is the non-zero entry is 1, the corresponding column entries are 0. Okay, did. Now look at the second row, we scan it. So what will get? The non-zero entry is minus 3. Therefore, we have to make this to 1. Therefore, what we have to do? We have to divide minus 3. So therefore, we get 1 minus 2, 1, Now the second row I am going to do.
Sir, last entry is 3, no, sir?
Last entry 1 minus. So what is R1 minus R3?
There you have -2, sir, not 2, sir.
Oh, sorry, sir. Okay, thank you. So this is minus. Therefore, this is minus 3. Yeah. Sorry, plus 3. Right? Yeah, this is 1
Yes.
minus minus plus. So now look at the first row and second row and third row. Both are equivalent, same. Therefore, just add or subtract second row, third row. We get the last row. We can make 0, 0. Okay, so what I am doing here, third row is nothing but just adding or subtracting second row and then third row, we get 0. What about the second row? We got to multiply minus 1 by 3. Minus 1 by 3 times the second row. So therefore we get 0, and here minus multiply means 1, and this is minus 1. Now we have to make the above the entry 0. Therefore finally we get, just you have to multiply this second row by 2 and then add. Therefore 1, 0, minus 2 means minus 1, and 0, 1, minus 1, 0, 0, 0. Right? So this is a row reduced echelon form. Now we have to multiply this vector v1, v2, v3 equal to 0, 0. Now simplify this, solve this equation. If you multiply this, what you get? v1 minus v3. So v1 minus v3 equal to 0. So if you multiply the second row, you get v2 minus v3 equal to 0. Okay, therefore what is from this, what you get? v1 equal to v3, and this from this v2 equal to v3, but v3 is nothing but v1. Therefore all the numbers are same. Therefore if you take any vector, all the entries are same, but except 0 vector, because we take 0, 0 is not allowed for eigenvector. Therefore if you take any vector, all the positions are 1. Therefore, for example, if you take 1, 1, 1, 2, 2, 2, 3, 3, 3, you can take anything. In general, I am taking, suppose, okay, 1, 1, 1 is an eigenvector, one of the eigenvector. Eigenvector of the matrix A corresponding to the eigenvalue lambda equal to 3. Not only take 1, 1, 1, you can take 2, 2 also. That is also a eigenvector. Therefore, what are the eigenvectors? You can take x, x, x. Okay, x is any real number. If you take x, 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 okay, you are collecting all these three people where x is varies over r different 0. You are not allowed to take this one. So this collection, all the elements from this collection is an eigenvector. Okay, why this is an eigenvector? You satisfy the equation. You just multiply with this, what is the given matrix is 1, 1, 1. So if you multiply with this x, 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 we get lambda times x, x, x. So for example, 1, 1, 1, 1, 1, 1, and this also 1, 1, 1. This is a matrix. Our V is x, x, x. So x, x, x. Now if you multiply these, we get 1 into x, 1 into x plus 1 into x, 3x. So all the terms you will get 3x, 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 3x. You can take 3 outside. Therefore, x, 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 x. Therefore, we get AV equal to 3 times V, where V is nothing but this x, x, x. Therefore, this is the eigen vector of A corresponding to the eigen value 3. So similarly, we can find an eigenvector corresponding to the eigenvalue 0. Okay. So, but the eigenvectors are always non-zero. Okay, keep in mind. So this is a method to find. So therefore, eigen vector of a matrix corresponding to the eigen value lambda are nothing but the solution, the non-zero solutions of the system of homogeneous equation. This is very, very important. So otherwise, you can saying a non-zero V satisfying the equation AV equal to lambda V. A non-zero V satisfy the condition AV equal to lambda V. Then we say V is an eigenvector corresponding to the eigenvalue lambda. Equivalently saying that eigenvectors of A corresponding to lambda is nothing but the non-zero solutions of, because eigenvectors are always non-zero. Keep in mind, that is very, very important. Okay. So therefore, this is a method or a procedure to find the eigenvectors of a matrix. So there are maybe for some repeated. So there are here in this case we have a eigenvalue 0. The multiplicity is 0. The multiplicity is 2 because 0 repeated 2 times. So in that case, there are some generalized eigenvectors there. Maybe we will study after introducing the linear transformation, all the things. Okay. Okay. So for any doubt. So now we did the eigen vectors. So any doubt? No. Okay. So the properties of eigenvectors, maybe once we discuss about subspace, all the things, we will define what is properties of the eigenvectors. Okay, so these eigenvectors are form a basis, provided the eigenvalues are distinct. The corresponding eigenvectors are linearly independent set and then base, all the things. So for that we define what is linearly independent, what is linearly dependent, all the things. So quickly we recall the basic things from group theory and ring theory, field theory, and then we move to the definition of uh, vector space. So first we discuss what is group. So quickly I'm discussing what is group. So group is a set together with one operation. Okay. So what is a group? A non-empty set G together with one operation. Usually we can simply take plus. Okay. So G under addition, we say this is a group. When we say this is group, then satisfy the some three axiom. One is associative, that is satisfied A plus B plus C equal to A plus B. First we add A and B and then add C. Both are equal for any A, B, C in the group element. And then second one is identity element exists. That is, there is an element, otherwise you can say there is an element E or with 0, the group G, such that A plus 0 equal to 0 plus A, you will get E. So this is identity element. And then this is with respect to addition. That's why I'm writing. So what is the inverse? So A plus minus A equal to minus A plus A equal to 0. Then we say this A minus A is the inverse. This is not only inverse, additive inverse. Additive inverse of A. So a set together with this operation satisfy these three property, then we say G comma plus is a group. Okay. Suppose the group satisfy the extra condition A plus B equal to B plus A, the commutative property, then we say it's an abelian group. Okay. So this is just a quick introduction of group. Next, suppose so here we add one algebraic structure, only one algebraic structure, that is only one operation here, that is plus. On a set G, we get a group structure. Suppose you are included two binary operation on a set, you will get a new algebraic structure, that is we call the ring. So ring is nothing but, again, suppose a non-empty set together with the two binary operation, usually we call R, with the usual some addition and then multiplication. So we say this is a ring, then we satisfy some property. So simply saying, with respect to addition, the set form an abelian group. So we know what is abelian group is with respect to addition. Now with respect to multiplication, the set R with respect to multiplication form a semi-group. Semi-group means what is satisfied up to associative property. So that is we called semi-group. So semi-group means what? It's just A into B, A into B into C equal to A into B into C. Satisfy only the associative property. So that is a second thing. The set with respect to multiplication form is semi-group. And third one is the distributive laws. Distributive laws. So there are, that is distributive law says there is a relation between this multiplication and addition. So that is A into B plus C equal to A into B plus A into C. Otherwise, A plus B, the multiply with the right hand side, C is nothing but A into C plus B into C. So this is a relation between this addition and multiplication. So this is we say distribution laws. So a ring is nothing but satisfy these three axioms, set of axioms. Suppose it need not be satisfied A into B equal to B into A. Suppose the set satisfied A into B equal to B into A multiplication with respect to multiplication for any element A comma B in the ring, we say R is a commutative ring. In general, this property need not be held in general ring, but some rings satisfy this condition with respect to multiplication. That ring is called commutative ring. Don't say abelian ring. So commutative means what is with respect to multiplication satisfy the property A B equal to B. Okay. So suppose some ring contains an element 1, satisfy that is 1 dot A equal to A dot 1 equal to A. If you take any A in the ring, you satisfy there is one element namely 1, satisfy the property, then we say R is a ring with identity. R is a ring with identity. So this one is called identity or sometimes called unity. Ring with unity or sometimes called ring with identity. Again, not all the rings contains this identity. Okay, some ring, for example, if you take 2z, multiples of 2. Okay, 2 plus or minus 2, plus or minus 4, all the things, right? That is 2z. That is a ring, but not a, if you take 2z. So 2z means 0, plus or minus 2, plus or minus 4, and so on, all multiples of 2. This is a ring. Even it's a commutative ring, but this is not a ring with identity because 1 is not there. Therefore, maybe some ring does not contain the unity. Okay, so if the ring contains the unity or identity, we say a ring with identity. Okay, now we did a second structure, algebra structure ring. Suppose this ring is said to be integral domain. So integral domain means what? If we take any two non-zero element, the product should be non-zero. Okay, so integral domain means what? So we say a commutative ring is said to be integral domain. So integral domain means the R should be commutative ring with unity. So a commutative ring, so a commutative ring with unity or with identity is said to be an integral domain. If it has no zero divisor, it has no zero divisor. So zero divisor means what? An element A is said to be zero divisor if there is a non-zero element, other non-zero element such that the product is zero. Okay. So what do you mean by zero divisor? When we say an element is zero divisor, so zero divisor means what? A non-zero element A is non-zero element in the ring is said to be zero divisor. Is said to be zero divisor if there is another non-zero element in the ring, there exists B not equal to 0 in the ring R such that the product is 0. Such that, but A into B is 0. But A is non-zero, B is non-zero, but the product is 0. That is possible. Okay. So why? Because if you take matrices, if you take some 2 by 2 matrix, both the matrices are non-zero, but the product is 0. For example, if you take 1, 0, 0, 0. So this is a non-zero matrix because at least one entity is non-zero. Therefore, this is non-zero matrix. I take this is A matrix. Suppose I am taking B is 0, 1, 0, 0. So this is also a non-zero matrix because at least one entity is non-zero. Now, what is the product? You get 0, 0, 0. Therefore, A is non-zero, B is non-zero, but the product is 0. So this A is called zero divisor. B is also called zero divisor. Okay. Because AB equal to B, the integral domain. Commutative premise always satisfied in the integral domain. So an integral domain is a commutative ring with unity is said to be integral domain. It has no zero divisor. If the ring does not contain any zero divisor, we call it an integral domain. Suppose a commutative contains the zero divisor, we cannot say it's an integral domain. It is not an integral domain. Okay. Now, what is field? When we say a commutative ring is said to be field, So definition of field. Field is nothing but first of all it's a ring. So we usually call F, but anyway we can use the same operation plus and dot. So when we say this ring is a field, first one is simply saying with respect to addition is form an abelian group. With respect to multiplication also form an abelian group, but you have to remove 0. You have to remove 0 from F. Now with respect to multiplication, this form an abelian group. That means what? Every non-zero element as a multiplied inverse exists, identity element exists, commutative property satisfied. And then third one is distribution law. As I simply saying F comma plus comma dot is a ring, is a commutative ring with unity, and every non-zero element has a multiplied inverse. Otherwise, you can say this one satisfied two distributive laws. So this is a field. So examples of fields are now in our case there are two basic examples are examples of fields are rational numbers. So rational numbers, real numbers, complex numbers are fields, but it's all infinite fields because it contains infinite number of elements. Therefore, it's a infinite field. These are all infinite fields. Now, what is a finite field? If you take the ZP, integer modulo P, it contains only P elements. So, how they look like? It's element 1, 2, 3, etc. P minus 1, or sometimes called 1 bar, 0 bar, 1 bar, 2 bar, etc. This is also a field. This is a finite field. But maximum we are using either R or C. Okay, in vector space, maximum use R or C, but you should know other fields also Q and then ZP, where P is a prime number, is very important. So here P is a prime number. If you take composite number, that is not a field. Okay. Now we define all the basic things: group, ring, field. Now using this field, we can define what is vector space. So when we say a set is a vector space over some field F, so hereafter we call F means what? A general field, but basically we can use either C or the real number R. But definition is for general thing. So now we define what is vector space. Vector space is also one of the algebraic structure. So again we have a set and we are going to impose two operation. One operation is plus, okay. Another operation is I am going to define this dot, but this dot is not a multiplication. This is actually scalar multiplication. So we know some set, and then we are going to define the operation. The operation is plus and then minus, plus and the dot. So when we say this is a vector space, we say it's a vector space over a field. See, without field we cannot define vector space. Okay, over the field something, either Q or C or anything. Generally we can take F, but field also two operation. One is plus and then multiplication, right? Therefore we differentiate that plus and then this plus. So this plus and then this multiplications are different. Okay, that's why I'm using different color. This addition not same as this addition. Again, this multiplication is not same as this multiplication. Both are different. So these are all different addition and multiplication. Now, what is this addition? We define usual addition. So with respect to, so when we say this is a vector space over the field, first one is, so this V with respect to addition form an abelian group. So that means what? Given any element x comma y in V, the sum should be in V. That is the operation here. What is, so therefore plus the operation plus, and then the other operation is this scalar multiplication. So actually it's a function from, this plus is a function from V cross V to V. But this dot is a function from F cross V to V. The function from F. So that is field F cross V to V. So this is addition. So this is a scalar multiplication. This dot. So don't use this color, blue color. Yeah. So that means what? What is this blue color multiplication? We take any element alpha from F and V from the vector V from the set V implies the product alpha times V should be in the set V. With respect to these two binary, these two operation, first of all, with respect to addition, we form an Abelian group, and then there is a relation between this multiplication, the elements of F and then B. So there are some. So I leave it to that to you. So go through the book, you will get a property that is you have to check some alpha times some element. This is nothing but alpha into x plus alpha times y. But this multiplication is actually here. This is a blue color multiplication. Addition also blue color addition, because with respect to vector addition is blue, scalar addition is what is the color I'm using? Green color. So actually, if you differentiate this, so alpha times this equal to alpha x plus beta alpha times y. Suppose fourth property alpha beta times x. Okay, so that means what I'm saying here alpha plus, but the plus is scalar plus. Suppose we are adding two scalar alpha into b. So this is actually x. So we have to multiply with this is which color? Green color. Because one scalar, one vector is we have to multiply scalar multiplication. This is equal to again alpha times x plus beta times x. So here we have a blue color multiplication. So we differentiate what the again here what is the addition? This is actually vector addition, because once you multiply with alpha into x, this alpha x is a vector and this beta x also a vector, therefore this is vector addition, and here also vector addition, but here alpha beta is a scalar addition. That's why I put the different color. And then suppose if you take a multiplication, suppose you multiply with some scalar, you get suppose alpha times beta times x equal to, I'm saying, alpha beta x. So that means what? What is the operation between these? So between this beta and x is a scalar multiplication. Again, for this one is scalar multiplication. Again, this once you multiply with the beta with x, we get vector. Therefore, this is a scalar multiplication. But here, alpha into b should be scalar multiplication. This alpha into this green color. So this alpha into b is that multiplication, and this is different multiplication. So keep in mind. So these two operations are different. So this plus and then this plus are different. So again, this multiplication and this multiplication is different. Okay, anyway, so we satisfy this property, then we say is a vector space over F. Okay, now subspace means what? When we say a subset of a vector space V is said to be subspace, then the subset itself is a vector space over the same field. So what do you mean by subspace? Okay, so examples of vector space, maybe if you take Rn, generally if you take any n, Rn is a vector space over the field R, over R is a vector space. Again, if you take complex number Cn, is a Cartesian product, this is also a vector space over, you can see R as well as over C. R over you can see is over rational numbers also we can see. Okay, so we can see Rn is a vector space over R. You can see Rn is a vector space over Q also, but you cannot see over C. Okay, because does not satisfy the scalar multiplication. Anyway, so I leave to the examples of vector space to you. So just to go through the book, you will get the definition. Now, what do you mean by subspace? So suppose we have a subset W of a vector space V. So what is the given? V is a vector space. V is vector space over the field F. Okay, suppose we take some non-empty subset. W is a subset of V. Then W is a subspace. When we say W is a subspace of V, then W itself is a vector space. The space of V if W, that the same addition, the same multiplication on V is a vector space over the same field. Vector space over the same field F. Or need to check all the things. So simply we have to check yes, subset is subspace or not. We have to check two conditions. One is if you take any element W1, W2 in W, the sum should be in the W. W1 plus W2 should be in W. And then second condition we have to check if you take any element alpha in F and then W in W, if W1 in W1, W implies the product alpha into W1 should be in W. So we have to check these two conditions. Then we say, and then 0 should be there. That is very important. Anyway, it's clear from the first condition. If you take W2 equal to W1 or W2 equal to minus W1, you will get a 0 there. Therefore, 0 should be there in the any subspace. If a subset satisfies these two conditions, we say W is a subspace of a vector space V. Okay. So any doubts so far? Okay.
Sir, generally what is a subspace, a vector space, sir? It means it's only a group, sir.
No, first condition should be group with respect to addition. A set with respect to addition, first they form a group, abelian group. And then there is a relation between that one or the field element. So the property 2, 3, 4, 5 satisfied. So first is with respect to addition, they form a group. That is the first definition, first condition. When we say V comma plus comma dot is a vector space, first with respect to the first operation plus the set forming abelian group. But with respect to, we cannot define this operation on V because look at the operation here is a function from V cross F to V. It's not a binary operation. Binary operation means what? It should be same set, V cross V. But here F cross V. Therefore, it's not a binary operation. Therefore, we call it a scalar multiplication. So therefore, now with respect to this scalar multiplication dot and with respect to addition, we satisfy some property. There is a relation between addition of scalar, addition of vectors, and then the scalar multiplication, and then addition of scalar with the scalar multiplication. Satisfy these properties, then we say V is a vector space over the field F. This is not a ring. Okay, for ring means we need a multiplication, usual multiplication we need for defining ring. Okay, but this vector space need not be a ring. It's anything, any structure. But the field is a ring. We are taking over the field. Field is nothing but this is a special type of ring. Okay, every non-zero multiplication. But this V is need not be a ring. Is just a group with respect to addition, and then satisfy the another properties 2, 3, 4, 5, and sometimes they will take one more condition. If suppose 1 into V is any element, 1 is a scalar, we get 1 into V equal to V. Usually they will write. So if these properties are satisfied, then we say V is a vector space over F. Okay, therefore, generally vector space means first condition satisfied with respect to addition is form a group. It's an abelian group. That is with respect to addition is satisfied the associative property. With respect to addition is satisfied the identity property. With respect to addition satisfied the inverse property. With respect to addition satisfied the A plus B equal to B plus A. But no need to check multiplication because this is not a scalar multiplication. This is just this is not a usual multiplication. This is scalar multiplication. Therefore, you no need to check if we take any two elements in V, the product is in V, we cannot define that. Because we cannot product two vector element. We can product one scalar element. So the elements of V is called vector. The elements of capital F is called scalar. So scalars are nothing but elements of capital F. And then vectors are nothing but the elements of V are called vectors. We can add two vectors, but we cannot multiply two vectors. But we can multiply one vector, one scalar. That multiplication is called scalar multiplication. But we can add two scalar, we can multiply two scalar because in the field we have a usual addition, we have a multiplication there. So There we can define addition and the multiplication. We can add to scalar, we can multiply to scalar. But in vector space, we can add two vectors, but we cannot multiply two vectors. But we can multiply with one scalar and then one vector. That is called scalar multiplication. Okay. So maybe we will easily check that yes, it is a subspace or not. So maybe I will check quickly. We discuss one thing. So if you take examples of vector space. So I said already, if you take Rn, okay, Rn is nothing but set of all n tuples. So Rn is nothing but set of all n tuples, x1, x2, etc., xn. Every element in Rn is a n tuple where the xi's are real numbers. Okay, so actually no need to write here because we are defining set of all n tuples where each xi comes from the real number. Now we can adding two n tuple, right? So how we can add? Suppose x1, x2, etc. xn is a one n tuple, and suppose we have another n tuple y1, y2, etc. yn. So we define is term by term. So that is x1 plus y1, comma x2 plus y2, etc., comma xn plus yn. This is the addition. Now suppose if you take some scalar alpha in the field F, and then if you take any element x equal to x1, x2, etc., xn in Rn, how we will define this scalar multiplication? Alpha times x, where x is nothing but this n tuple. So nothing but you have to multiply alpha to the each term. Alpha times x1, alpha times x2, etc., alpha times xn. Now with respect to this scalar multiplication and with respect to this addition, then Rn plus dot comma this scalar multiplication is a vector space over the field R. Okay. You got to check other conditions also, all other properties of all other axioms of vector space. So you have to define what is addition, what is the scalar multiplication. With respect to these two operations, we have to check satisfy all the axioms of vector space or not. Here the field elements I am taking Q, sorry R. You can take the smaller field Q also, but if you cannot take complex number. Why we cannot take complex number? Suppose this is a vector space over complex number, what will happen? That scalar multiplication is not defined. Why? Because if we take some scalar, so I am taking I from the scalar C. Suppose I am taking 1, 2, etc. something. Okay, so otherwise take 1, 1, 1, 1. Yeah, all the indices are 1. This is a vector. Suppose I am multiplying I means what? Should be I. But this is not an element of Rn. Okay, because each position is a complex number, therefore this is not a real number. Therefore, if you take our field is complex number, so this we cannot define the scalar multiplication. Therefore, it should be either R or smaller than R. We can take Q is a field, right? Therefore, we can view this Rn is a vector space over Q, as well as we can see this Rn is a vector space over R. But we cannot see this Rn is a vector space over C. But if we take C power n, that is all n tuple, each positions are complex number, there we can see C power n is a vector space over C, or C power n is a vector space over R. If you take any smaller field, it's always form a vector space. Even C power n is a vector space over Q, is always satisfied because this smaller field Q, R, these are all subset of C. Okay, we can do that. So in R2, if you take the special case, in R2, this is true for any n. Suppose I am taking n equal to is a single set of all ordered pair, so it's nothing but our plane. So this R2 is a vector space over R. Okay, so if we take the specific case, R2 is a vector space over, I am taking now R. Now what are the subspace? So if you look at this, this is our R2, okay. So this is x-axis and this is y-axis anyway. So all the subspace must contain 0, okay, because it's a subgroup, therefore should be 0, should contain 0. If you take any subspace, it should contain 0. And here vectors are linear actually, so therefore I'm listing here. So the subspace of R2R is nothing but all any line passing through origin. If you take any line passing through origin, this is a subspace. Or if you take any other line passing through origin, this is also a subspace. Or you can take any other line like this is also a subspace. Therefore, the subspace R of R2 are line passing through origin. So now it's just line, not a curve. Parabola is not a subspace. Why parabola is not a subspace? Suppose I am drawing parabola. Simply I am taking this our parabola means passing through origin. This is not a subspace. Why this is not a subspace? Suppose you are taking 2 points on the curve. Suppose I am taking 1 point here. Suppose I am taking another point here. Suppose I am taking x this and this is y. But x plus y may be somewhere, not on the curve. Okay, therefore x comma y and the parabola w, but x plus y need not be in the set. Maybe somewhere, maybe here or anywhere. It's not on the curve. That's why we take the linear curve. But if you take the straight line, if you take any point on the straight line, suppose in the suppose I am taking x here, and suppose I am taking some z here, suppose I am taking some other a here and b here, a plus b should be on the curve, on the line, it's anywhere, but should be lying on the line. That's why the lines are subspace. Therefore, in R2, the only subspace are subspaces are lines passing through origin. That is important. Passing through origin. Suppose if we case R3, suppose we go R3, what are the subspace? So in R3 we have two structure. One is line, another one is plane. Okay. Therefore, in R3, clearly R3 is a vector space over R. The subspace are line passing through plane, line passing through origin or plane passing through origin. So line, the only subspace of R3 are lines passing through origin. Only subspaces of R3 are lines, any line. So lines passing through origin or plane passing through origin. If we take xy plane or yz plane or zx plane, any plane but passing through origin. Passing through origin, and so lines passing through origin and plane passing through origin. These are the only subspace in R3. Therefore, when it subspace means first condition should be satisfied. It should be 0 should be there in the set. Okay, so for suppose I am taking some, suppose I am asking the question, I am going to write one thing. So W equal to set of all x comma y comma z in R3. We are collecting the tuple. What is the condition satisfied? It should satisfy a b are fixed. So a x b y plus c z equal to 0. So I am questioning is W is a subspace? Is W a subspace of R3? And we know the subspace of R3. So subspace are, so what is the equation is? What is the equation represent? It's a plane equation. And then the left, we have right hand side is 0. Therefore, this is a plane passing through origin. Therefore, clearly W is a subspace. Okay. So in R3, if you take line or plane passing through origin, it should be a subspace. Okay, you just to go through that some book, you will find some exercise to solve this set is subspace or not. Okay, so suppose quickly I am asking one question. We have some other set W1. I am taking again is an element of x, y, z in R3, such that what is the condition this satisfied? The product should be 0. Is this subspace of R3? So we cannot say this xy z represent maybe anything. It's not a plane, right? It's not a line. It's not a line equation. This is not a plane equation. But we have to check that. Anyway, 0, 0 should be there. If you suppose we are going to say a set is subspace, 0, 0 should be there. That means 0, 0 satisfies this condition or not. Yeah, product of this should be 0. Therefore, 0, 0, first condition you have to check that 0, 0 is there or not. Yeah, it is there. That is not enough. Then if you take any two elements, the sum should be in the set. So suppose I am taking 1, 1, 0. Clearly this is an element in W1 because if you take the product, you will get 0. Suppose I am taking 0, 0, 1. This is also in an element of W1 because the product is also 0. Now just I am adding this. What you will get? 1, 1, 1. But what is the product? We get 1, but it's not satisfied the property. Therefore, this element is there, this also is there, but sum is not there. Therefore, this is not a subspace. Is not a subspace of R3. Okay, so first condition we have to check 0 is there or not. So if it is 0 is not there, you can easily say it's not a subspace. If 0 is there, next we have to check if we take some two arbitrary element or some particular element, sum should be there. Again, if sum is there, now next we have to check scalar multiplication. If we take some scalar alpha and then we take some particular element from the set, if we take the product also is the scalar multiplication also is in the set, means okay, this is a subspace. Okay, this is a 3-step. First we have to check 0 is there or not. After that you take the addition. If you take two elements, the addition should be there, and then scalar multiplication should be there. Okay. Now maybe finally I will ask one question. Please tell me that this is a subspace of R3 or not. W2 I am defining. So collection of all ordered triple x, y, z in R3 satisfy the condition that x square plus y square minus z square equal to 0. So you have to square the first coordinate, then you got to square the second coordinate and sum it, and then subtract the third coordinate square. Is this clearly, if you substitute 0, 0, 0, 0, 0, 0 satisfied the equation 0 square plus 0 square minus 0 square is 0. Therefore, this is an element of W2. Therefore, 0 is there. Now, next we have to check that sum is there. If you take, so first you have to think that this is not a subspace. Then you have to try to give the counter example. Okay. Suppose I am giving that x equal to 1, therefore 1 comma 1 comma 2 is in W2, right? No. I am taking 1 square, we take 4. So give some element to satisfy this equation. 1 square, 2, but this is I am taking, suppose I am taking root 2. Okay, because everything is a real number, right? So therefore 1 square plus 1 square is 2, minus square root square is 2, 2 minus 2 is 0. Therefore 1, 1 root 2 is an element of this set. Got it? Suppose I am taking 1, 1 minus root 2. Is this the set W2? Because I am squaring Z, therefore it's always there. Right? Now what is the sum of these two vectors? Term by term. So 1 plus 1 is 2, 1 plus 1 is 2, and this plus this 0. But this is a vector in this is not an element of W2, because if you square the first coordinate is 4 plus the second coordinate square is 4, but the third one is 0, we get 8, but this is not a 0. Therefore, sum is not there. Therefore, this is not a subspace. It's not a subspace of R3. Okay. So you try to solve some problems in the exercise from the book. Okay. Now I stop the class. Thank you.